Good morning, everybody. I want to welcome you all to this edition of the Potter's Roundtable. This is a continuation of some of the topics we've done before, basically having to do with glaze chemistry. And specifically today, we're going to be talking about understanding glaze recipes.
Welcome to the Potter's Roundtable, a monthly podcast where we share our passion for the ceramic arts and a collection of topics specific to potters. Remember to subscribe so you don't miss a single episode. Enjoy the show.
Specifically today, we're going to be talking about understanding glaze recipes, because I thought that if you're interested in glazes, probably the first thing you may run across is you see the recipe for a glaze, and so there's a lot you can tell just by looking at a recipe. That's one of the points we'll make as we go through the discussion. If you get familiar with some of the raw materials that are used in glazes, there's a lot. You can just look at a glaze recipe and you can tell a lot about the glaze. And I'll point that out as we get toward the end. You'll see, and some of the even problems that occur with glazes, you can just look at the recipe and go, oh, well, that's the reason why that problem happens, because there's something about the glaze recipe. So that's we'll talk about that. So let's start. First of all, what is a glaze? Well, basically, a glaze, this is a little background information. A glaze is basically a glass. And you might say, well, what is glass? Technically, a glass is a material where the atoms are arranged randomly, as in a liquid, rather than in an orderly manner. And I've got a couple of examples here. Like, if you imagine these are atoms in this jar, a liquid, this is basically what a liquid is like. The atoms or the molecules are free to move around, and that's why the liquid can flow, because the atoms are sort of, they're attracted to one another, but they're free to move and just roll around and slide around, okay? In most materials that are crystalline, or crystals form, like a solid, the atoms are arranged in a regular pattern like this. There are lots of different patterns that the atoms may be arranged in, but there's an organization to them. They're not just random. But a glass is like a frozen liquid. A glass looks like this, where the atoms do not have a regular array like this. The atoms are randomly arranged. And the reason why that's important is it really affects the properties. One of the properties, for example, is that most materials that are crystalline, or crystals like this, have a definite melting point. When you heat them up, you get to a certain point, they melt, like ice is a good example. Okay? But glasses, a lot of glasses don't. They don't melt at one specific point. As you heat them up, they get softer and softer and softer and softer, and finally they get runny, and finally they turn to liquid. So that's just one of the properties, and that's due to the fact that the way the atoms are arranged. So glasses have very unique properties compared to crystalline materials. And that's fortunate for us, because if they were crystalline, we wouldn't be able to use them as glazes. Okay? So glazes are basically glass. And most of the glazes that we use are silicate glass. They're called silicate glasses because they're made primarily of silica. And silica is a really common material. It's also the material that you may have heard of, the mineral quartz. I've got some, by the way, those examples on the table back there, you're welcome to look at those. Those are examples, we're going to be talking about the raw materials that go into making glazes, and those are examples of the actual raw materials. And I wanted people to be able to look at those so that you don't, because normally people think of, like Wollastonite is a white powder in a jar. Well, it isn't. It's actually a mineral. Or Nepheline Syenite is a rock. Well, what does it look like? Well, I have examples back there. And I also have several examples of quartz or silica back there. So most of our glasses, if you're interested in the chemistry, the formula for silica is that. It's silicon dioxide. And all of our glasses that we use for glazes are based on silica. They're mostly silica. And they're made from, industrially, they're made from sand, for example. They'll dig up quartz sand or silica sand, and that forms the basis with other materials, forms the basis for the glaze. Okay? There are, most of the glasses that we use are used for glasses and dinnerware, and we think of window panes and all the other uses we have for glass are man-made, but there is also a naturally occurring form of glass. This is thanks to Sally. If you haven't seen this, volcanic glass or obsidian is a glass. This is a piece of obsidian that Sally gave me from Oregon. And the interesting thing when you look at this particular example, if you're familiar with what are called Temuku glazes, this looks an awful lot like a Temuku glaze. And actually, in composition, it's very close to a Temuku glaze. But if you haven't seen it, this has some sharp edges, so don't sort of throw it around in your hands, because I don't think we have enough Band-Aids to cover everybody. But this is a naturally occurring glass. It's volcanic glass. Okay? Okay, so how do glazes, when we're making glazes, how do they work? Basically, we take a combination of raw materials. They might be minerals, they might be chemicals. We mix them together in certain proportions, and we heat them until they all melt together. And then, so that on the pot at high temperature, the glazes are actually liquid. If you could reach into a kiln at high temperature and like wipe your finger through the glaze, it would be like honey. And they're generally also clear. When they're melted, it would be like, literally look like honey on the pot. And then as the kiln cools down, the glaze basically freezes. And the important point here is, in a lot of other materials, if we melted it and we cooled it down, the glaze would crystallize. It would form crystals. But because of these particular compositions, they don't. They freeze into this random arrangement, and they form a glass. And that's the glaze. So the glazes on pots is a coating of glass that we have applied to the pot. This is probably, when we talk about a glaze recipe, these are cone 10, they happen to be cone 10. This first one for a celadon glaze, this is the classic Asian sort of clear green glaze that you see in a lot of places. And so when you see a recipe, this is typically what you may see, a list of ingredients. I've listed the names of them here: Custer Feldspar, whiting, EPK, Flint, and red oxide. And I've also just incidentally put down the chemical formula for them. And so the formula should be written as this. The W/O means weight percent on the basis of weight. So this is the way you might see a recipe. And then below it is another recipe for a cone 10 glaze called green crackle. And I've listed, you notice there's two different columns. And the reason why is one of them is written correctly and one of them is not. The proper way to write a glaze recipe is on the left, where what's called the base glaze, the ingredients total 100%, and then any other additives or modifiers or things that sort of affect the appearance of it are put in addition. So on the glaze on the top, celadon, you notice the red iron oxide is included in the 100%. It really shouldn't be. It shouldn't be listed that way. It should be listed that it should be 27 plus 19.5 plus 19 equals something or other, and then the 100 is added below it, the way I've done with the green crackle. So on the right-hand column for the green crackle, that's the common way you see it, but that's the incorrect way of listing the glaze. Because the additive, the yellow ochre is a form of yellow iron oxide. That's the colorant. And so that shouldn't be included. So one of the things we're going to be talking about is, when we talk about glazes, there's the base glaze. That's the basic components of the glaze that determine really the important properties of the glaze, the melting point, whether it's shiny or matte, all the fundamental properties of the glaze. And other things like color or whether it's opaque are really just additives that are put on later. So it's a really good idea to separate the base glaze from the modifiers of the additives. And you can kind of think of it like paint. You know, when you go to the hardware store now and you buy almost any color, there's a paint base they use, and then that base is the same regardless of what the color is, and then you add the special colorants or the modifiers to it. It's kind of the same idea, where you have the base glaze that determines the basic properties. Like, for instance, because the reason why I say that is this little bit of red iron oxide or the yellow ochre is not going to affect the properties of the glaze, like the melting point, at all. It's just going to affect the color. So we really want to distinguish between the properties that really control how the glaze behaves. How does it melt? Is it runny? Is it matte? Is it that sort of thing, from just these some of the sort of more visual characteristics. So I guess one more point I want to make on that, in relation to this, is go to the next page where it says converting parts to weight percent. This is a handwritten page because I was too lazy to type it out. Everybody have it? Yeah. Converting parts to weight percent. The point here is, my example that I gave you with celadon, or even with the green crackle, those were all at least listed as percent. Is everybody familiar or comfortable with the concept of percent? If you're not, please, say so. Okay. Percent is basically the fraction based on 100. It's like how many parts out of 100. That's basically what it is. So it's like if you have 100 parts, how many parts out of the 100 are each particular item? And the nice thing about it is, if you base something on percent, then if you were weighing out a glaze recipe, if the recipe is in percent, it doesn't matter whether you're weighing out in pounds or you're weighing it out in grams, and it doesn't matter even the size. It's essentially the proportion if it's parts out of 100. So it doesn't matter if the weight percent is 10%. It doesn't matter whether you're weighing out a 100-pound batch or a 1-pound batch. The proportion is the same. That's the whole. So it gets rid of. So it ignores units. That's the important point of it. It just tells you what the fraction is, regardless of what the unit. It could be handfuls. It could be shovelfuls. It doesn't matter. Okay. Okay. So on this page, converting parts to weight percent, it's very common to see recipes where, unlike my celadon or my green cracker recipes, where at least I have them totaling 100%. When you look at the numbers, they don't add up to 100. They may be more than 100, they may be less than 100. And so here's an example of another recipe, Custer Feldspar whiting. EPK, by the way, in case you're not familiar with, that stands for Edgar Plastic Kaolin. That's a kind of kaolin. We're going to talk more about these. And then Flint is silica. That's another name for silica. So here, these numbers that you see in the recipe add up to 300. So they're obviously not percent. So the question is, how do I convert that to percent? Because that, again, to make the recipe useful. What I do is, and this is go across the columns, the first thing I do is I take out the 3 parts of iron oxide because that's a colorant, right? That's not part of my base glaze. And I add up the others. So I have the Custer Feldspar, the whiting, the EPK, and the Flint adding up to 297. And then I divide each one of those numbers by 297, and that gives me percent. So 81 divided by 297 is 0.273, which is the same as 27.3%.
The parts is actually equivalent to the weight.
I don't know what it is. A lot of times you'll see a recipe that it doesn't say, it just says 81. What is that, 81 handfuls? 81 hatfuls? 81 wheelbarrows? They don't tell you. But in this case, I have to assume its weight. I have to assume its weight, okay? And a lot of times what you see these recipes, this will be a recipe that somebody used in a studio and they've used it over and over again and they mean grams, but they just don't even say it. So I have to assume it's weight though, because I'm doing it on the basis of weight. So if I so 81 divided by 297 is 0.273, which is the same as 27.3%. So now I've got those ingredients based on 100, and then I take the 3 grams from my red iron oxide and divide that by 297, and that gives me 1%, about 1%. I've rounded it off here. So I can convert. So regardless of as long as it's on weight, regardless of what those numbers are, I can convert the recipe to weight percent, and then it's a whole lot more useful. Because if I had this recipe where I've got 58.5 parts of whiting, and I wanted to make a 450-gram batch, you go like, how in the world do I do that? Well, if it's percent, it's easy. I multiply 450 grams by 19.7%, and that tells me how much whiting to use. Everybody follow that? You sure? Okay, well, the way I would use percent, again, percent is a fraction, right? It's basically, it's really called like a decimal fraction. So if here's my recipe, and I know that now the whiting is 19.7%, and now I want to make up a 500-gram batch of this recipe, and I want to know how much whiting do I use. I'd multiply 500 grams by 19.7%. The actual form I'd use would be 0.197, that fraction. Because 19% is around 20%, which is around a fifth, roughly a fifth, right? So that means that if I wanted to make up a 500-gram batch, roughly a fifth of that weight has to be whiting. So I take the recipe weight that I want and multiply it by each one of the ingredients, the weight percent in turn, to tell me how much I need to use. And the way to check it is, after you do that, is write the weights over, and then see if they do add up to the weight to the batch. If you've done it correctly, then after I multiply the weight by each ingredient, and I have the amounts, they should total up to 500 to the batch size again. If not, I've messed something up. And this is a really common way that you'll see recipes in a lot of books and references, is just I'm calling it parts. I'm assuming it's weight. but at least they don't add up to 100. And it's a really unuseful way to show a recipe because you can't compare it to anything else, and it's not even easy. And you still have to convert it to percent to figure out, if you want to make a different batch size. If I don't want to make a 300-gram batch and I want to make a 750-gram batch, it's like, how do I figure that out? Well, you convert it to percent. Basically, so what are these ingredients and what do they do? So what we're going to do is we're going to start with a little background information, and then we're going to look at some of the individual ingredients. First of all, some background information. What we really care about when we're talking about glaze chemistry are not the ingredients that we put into the glaze, but the oxides, the chemical oxides that are in the ingredients. An oxide is a chemical compound of some chemical element combined with oxygen. So this is an example of an oxide. Actually, silica is the element silicon plus oxygen. That's an oxide. So what we really care about when we talk about glaze chemistry is not the raw materials, it's the oxides that the raw materials contain. That's what we really care about. And it's the properties of the oxides that control the properties of the glaze. Okay? So we sort of think one step back, not the ingredients. What do the ingredients contain? That's what we care about. So for example, we use so I make the distinction between ingredients, which are the things we use to make the glaze, and the components, or what's actually in them. So for example, we use clay as an ingredient in a lot of glazes. Well, the reason why we use clay as a lot of ingredient is not because just it's clay, but because of the oxides it contains. It contains silica, and it contains aluminum oxide. That's why we use the clay, not because it's clay, but because we want these two oxides, silicon dioxide and aluminum oxide, in our glaze recipe. So that's why we use the clay. The same way we use, you may have heard of like the different kind of the mineral feldspar, soda feldspar. We use soda feldspar as a glaze ingredient because it contains sodium oxide, it contains aluminum oxide, and it contains silicon dioxide. So we're picking the ingredients because of what they contain. And the point here is that when we melt a glaze and when we fire a glaze and melt it, those ingredients are gone. You can't recognize those ingredients anymore. They're completely broken down, and the elements are recombined in new ways. So there's no longer any clay in a glaze recipe, in a melted glaze. It's gone. The components of the clay have recombined to form something new. Okay, so they're totally unrecognizable. When you fire a glaze, all that list of things, the talc and the silica and the wetting, they're gone. All the elements, they've been broken down, and the elements have recombined in a new way to make this glass. So that's why we don't care about as much. I mean, we do care, but ultimately when we're talking about the properties of the glaze, we're talking about how have these elements recombined in a new way, not what we put in to get them. Everybody sort of follow that? I mean, it's not exactly like baking, because I was thinking like when you bake bread and you put flour and sugar and stuff in, you can still kind of recognize that it contains flour. Maybe it's more like putting things in a blender. You're making a smoothie and you put leftover. I did this years ago for my kids. I decided I was going to take leftovers out of the refrigerator, so I made a liver, potato, asparagus smoothie. And, well, I thought, if you eat it on a plate, why can't you eat it in a blender? So yeah, it was liver, potatoes, and asparagus. And of course, in the final sort of army green smoothie that it produced, none of the original ingredients were recognizable. And actually it had new properties. So maybe it's sort of analogous to that, is the fact that the ingredients, you can't recognize the ingredients anymore. By the way, that's a little background information. And we're going to refer to this also, again, more about the oxides and what's in them. That's where the chemistry comes in. Okay. So there's another idea that I want to introduce here, or talk about a little bit about. There was a German chemist in the 1800s who was working in a porcelain factory in Germany. His name was Herman Seeger. And he was responsible basically for all the production of the porcelain factory. This is when they were making these really elaborate, beautiful porcelain sculptures and figurines and urns and vases, really fancy stuff. And he was responsible for basically the whole operation. If anything went wrong, it was his fault. And he was the one that was formulating the glazes. This was in the 1800s. We knew a lot about chemistry, but not nearly as much as we know now. And he was the ones that was in charge of firing the pots, basically the whole production. And what he realized was that he was one of the first people to realize that it's the oxides that we really care about, because he was a chemist. And he started thinking that when he started looking at glazes, we can group the ingredients, or we can group the oxides in a glaze into 3 categories. And we need those 3 categories in a glaze. And the 3 categories are what he called the glass former, and that is, what are the ingredients that actually make the bulk of the glass? And he called them the glass former elements. And we'll talk more about those. And in our case, it's silica. Our glazes are mostly made out of the compound silica. Okay, so that's the glass former for most of our glazes. And like, for instance, and that's the same thing, all of the common glasses that we use, window glass, drinking glasses, containers, those are all silica glass. They have slightly different properties from a glaze, but they're not that much different. They're all basically silica plus some other stuff. I mean, for instance, window glass is basically sodium oxide and silica and some calcium oxide, and that's it. And it has different properties. For instance, it melts at a lower temperature than our glazes, so that they can fabricate windows out of it. It has a little different composition. It's not as maybe chemically resistant as some of our glazes. It's not as hard, but it still is fairly closely related to our glazes. It's still basically a silicate glass. The second category that he identified was what he called fluxes. And a flux, F-L-U-X, a flux is something that helps something else melt at a lower temperature. This is a lump of quartz that I found in my backyard. This is really, you'll find this everywhere. It's really common. This is basically the heart of all our glazes. This is essentially almost pure silica. The problem is, if I want to make this into a glass, it melts at a really, really high temperature. So with our kilns that we have available for pottery, we can't melt this stuff. So we couldn't turn it into a glass. So what Seeger was saying was, there are certain chemical elements that I can add to this, and when I combine it, it lowers the melting point tremendously, like maybe almost half. So all of a sudden now, if I combine this with a flux, now with the kilns that we have available, I can melt this stuff and turn it into a glass. So that's what the fluxes do. They do with that important property of maybe allowing me to melt silica, because silica is a great glass former, but only if I can heat it to over 3,000 degrees, which we can't. So now I can by adding fluxes to it, okay? And the third category that he recognized was, we're going to talk a lot more about these, but what he called stabilizers. Because if you think about it, if I melt this stuff, I add a flux to it and melt it, and I heat it up to high temperatures, in some cases, it might have the consistency of water, and it would melt and just run right off my pots and make a mess. So I've got to have some way to sort of thicken it, make it more like honey or stiffer, so that yes, it melts, and yes, it flows and covers the surface of the pots, but it doesn't just drain off the pots. That's what a stabilizer does. A stabilizer essentially thickens when the glaze melts. It thickens it so it's not quite so runny, and it'll stay on the pot. And he realized that these are the 3 basic components, or 3 categories of materials you need to have in a glaze. You need to have the base of the glaze, the glass former. You need to have something or some things to help it melt. And then you have to have something to help control it so it doesn't get too runny and go crazy and run off all your pots. What Herman Seeger did was, in addition to this notion of these 3 categories, he also developed an alternative way to write a formula for a glaze, and it's called the Seger formula, or the unity molecular formula. And it's not based on weights, it's based on counting molecules. And like the proportion of molecules, like how many silica molecules do I need, or how many aluminum molecules do I need? And we'll talk a little bit about this. So if you go to the next page, that's titled the Unity Seger Formula. So this is how, these are all the elements, the common elements now that we use for making pottery. And so on the left-hand column under the fluxes, I've listed, and I've shortened it. I should say oxide, because these all should be talked about in oxides. And I've given the formula in terms of oxides, but for shorthand, so it would fit in the column, I just used the first word. So I've got, potassium, sodium, lithium, calcium, magnesium, barium, strontium, zinc, lead, and boron. And actually I mean oxides, so potassium oxide, sodium oxide, lithium oxide, and so forth. And those are the chemical formulas. So all of those elements as oxides act as fluxes. They help the silica, or they help the glaze melt. And then under stabilizers, the main stabilizer that we use is alumina. That's a shorthand terminology. It means really aluminum oxide. Alumina is kind of a geology chemistry shorthand for the term aluminum oxide. And that's the formula, Al2O3. 2 aluminum atoms, 3 oxygen atoms. And the glass former, the only one we use intentionally, really, or primarily, is silica, and the formula is SiO2, as I've written here. And the question you asked, Martha, about what's that at the top, RO, R2O, there is no element whose symbol is R. So the point is, if the formula of an oxide looks like that, RO, something O, or R2O, it's probably a flux. So for instance, if you go down like calcium oxide, in this case, instead of the R, I'm using Ca, the symbol for calcium. So if it looks like RO or CaO, that's probably a flux. Or if it looks like R2O, like potassium oxide, K2O, that's probably a flux. So just looking at the formula, there's a good guess as to what the function of that element, of that compound, is in the glaze. In the same way with stabilizers, R2O3, well, in this case, it's Al2O3, is the alumina. Now, what's interesting here is, this is a little detail, but for instance, there's another oxide that we use a lot for a colorant, iron oxide, which also has the formula Fe2O3. Well, even though we use it as a colorant, under some circumstances, Fe2O3 and iron oxide can act as a stabilizer. So it's not 100% clear cut on some of these things as to what function. A lot of these things have multiple functions when we're talking about what a glazing ingredient is. It may do more than one thing, and so we sort of have to keep that in mind. Okay? Now, at the bottom of this page, and I'm not going to dwell on this a lot, but at the bottom of this page is an example of one of Sieger's glaze formulas that you might never recognize as a glaze formula. And this is it, these 3 columns. And what he's done is he's listed the fluxes, the fraction of fluxes, so like half 0.5 CaO, 0.3 MgO, magnesium oxide, 0.2 potassium oxide, equal to 1. This is the format he worked out. And then in the middle column, it shows the stabilizers, aluminum oxide and iron oxide. And then the glass formers, it shows silica and also titanium oxide, TiO2, because that's also a glass former. And you might say, well, what's the value? Because you certainly can't make up a recipe from this. You can't weigh out a glaze because there aren't any weights. This is sort of ratios of molecules. If you put it in this format, what this allows you to do is compare glaze recipes. You can look at this recipe and tell what temperature it's fired at, whether it's going to be a matte or by looking at the proportions of these 3 different categories. So that's what when I say we won't dwell on it here, but that was the value of this format, this Seger formula. It allows you to look at the recipe and determine what the properties of the glaze are and compare it to other glazes. So it was like what are the ratios? It was very valuable for that. So the point is, you need all 3 groups in a glaze. That was a really important concept. You need to have all 3 groups to make up a glaze. And the properties of the groups affect or control all the major properties of the glaze. What's the firing temperature? What's the range of the firing temperature? You're probably familiar with some glazes. They have a very narrow firing range, and you can overfire them easily or underfire them very easily. And others are a lot more tolerant. They might be good for a wide. I've got a glaze, for instance, that I can fire from cone 6 to cone 14, and it comes out fine wherever I fire it. So some glazes have a very wide firing range, and others don't. So those properties are all controlled by the proportions and the identities of those materials in those 3 groups. Whether it's glossy or matte, we're talking about essentially the base glaze now. Whether it's glossy or matte, that's determined by those ingredients. Whether it's clear or opaque, that's determined by the ingredients. What the color response is. We have that list on the previous page of all those different fluxes. They affect how a colorant interacts with the glaze. So the copper in the presence of lithium flux is not going to give you the same color as copper in the presence of sodium. Nothing simple in pottery, as you're probably gradually starting to catch on. So just the choice of flux that you use to melt the glaze can change the subtle effects on the color that you get with the glaze. And it also has effects on things like crazing. Whether a glaze crazes or not is based almost directly on what the ingredients are in the glaze, which we'll talk about a little bit.
We hope you're enjoying the show. Please take a moment to leave a 5-star review on your podcast platform of choice. It really helps new listeners find the show. Don't forget to subscribe to receive updates as new episodes are released. And if you'd like to support the video and podcast production of the Potter's Roundtable, become a patron. Go to patreon.com and search for the Potter's Roundtable. Your support will help us achieve our goal of creating a digital library spanning the ceramic arts for use by educators and artists alike. Thank you for your support. Now let's get back to the show.
So let's look at a list of common glaze ingredients, and the point here is that we use these materials first of all because they're available and because they have a reasonable cost. There may be other, keeping in mind that we want certain, this is the one we're going to be looking at that says, this is one of the additional pages that says common glaze ingredients. That was one of the additional pages that Dennis produced. It may already be in your handout if you got one of my stapled copies, or it may not be. Everybody have it? Okay. So we use these particular materials because they're available and they're cheap. There might be other ingredients that we could, actual ingredients that we could use, but they might not, for instance, they might not be safe. Like we can get sodium oxide. I mean, it would be great if we could just use the oxides, but in most cases we can't. But you can get sodium oxide, but it's explosive and it absorbs water. I have to tell you a story. I worked in a chemistry lab one summer, and we were using sodium oxide as an ingredient as part of our testing. And we had a big can, and it has to be packed in metal because if it touches anything combustible, it explodes. So it came in a big metal can, but unfortunately it also absorbs moisture and gets kind of cakey. So one of the chemists I was working with, he'd worked there forever, and he'd gotten a little careless. We had this big metal can, like a 5-pound can of sodium oxide. So he took a big wooden spoon and he held the can under his arm and stabbed it into the can to sort of break the cake. And it went boom, blew the spoon out of his hand, blew this can of sodium oxide back across the room, and he was lucky he wasn't killed. Because just the impact of the wooden spoon with the sodium oxide caused an explosion. So we could get sodium oxide, for example, but we wouldn't want to work with it. So we work with these particular materials because they're safe to work with, they're fairly cheap, and most importantly, they still contain the oxides that we actually are interested in, okay? And these include, and we'll talk about it as we go through it, but these may be minerals, they may be rocks, they may be commercially made chemicals, they may be, some of these names are actually just brand names that don't tell you, unless you know what they are, you don't know what they are. So there's a whole, because of the way we've, sort of the whole pottery field, there's not a lot of logic to some of this. So you'll see some of these names, that's why there's such a variety of names to these things. So let's go down the list, let's talk about them a little bit. And again, if you have any questions at all while we're going through them, please interrupt me, say something. So these are common glaze ingredients in no particular order. The first ones I put down here, and by the way, again, remember, I have examples of just about all of these over there on the table. And as I say, to me, it's important to, part of this is getting familiar with a glaze and understanding the recipes and the ingredients is, to me, I also, when I do that, I'm picturing in my mind what the material is, not just a white powder in a jar, but what does it look like? And therefore, what are the characteristics of this material? It helps me remember even what they do to some extent, okay? So the feldspars, that's a family of minerals as the feldspars. And by definition, a mineral is a naturally occurring inorganic chemical compound. That's the definition of a mineral. A naturally occurring inorganic chemical compound. And what that means is, A, it's naturally occurring in nature. It's inorganic, meaning it's not much involved with life forms and carbon. There are two branches of chemistry, organic and inorganic chemistry. Organic chemistry has to do with living things and is largely based chemistry that involves carbon. And then there's inorganic chemistry, which is everything else. And so our bodies are organic chemistry, but our glazes are inorganic chemistry. So, and when I say naturally occurring chemical compound, the point there is minerals are not just an arbitrary sort of garbage pail of elements. You can write a formula for a mineral. They're very specific chemical compounds with specific proportions. They just happen to occur in nature, okay? So the feldspars, that's a family of minerals, and these are generally used as fluxes. And there are two categories that you'll see in glaze recipes, and they may be worded very differently. The general category is potash feldspar, which contains the element potassium. And this is where also the symbolism of chemistry can drive people crazy if you're not familiar with it, because the chemical symbol for potassium is K, from the Latin kalium for potassium. Because as the elements were discovered over the centuries, people would name them after people, after places, after Greek gods, after the Latin name or the Greek name or whatever. So there's this whole wide, weird range. So there's not necessarily any direct correspondence between the name. I mean, it'd be nice that potassium, why isn't the symbol P? Well, because that's already been used for something else. So in this case, potassium is K. So there's potash feldspar, which means it contains potassium, or there's soda feldspar, which means it contains sodium. Those are the two main kind of feldspars you'll see. Now that's just a general category of feldspar. A recipe might just say potash feldspar. But if you're going to buy potash feldspar, you have to actually buy a product from somebody. So Custer, what I've shown here, that's actually a brand name for a type of potash feldspar, probably one of the most common types, Custer Feldspar. And it's called Custer because it's mined in Custer, South Dakota. And it's a brand name like Kleenex or Scotch tape. So you might also see a recipe that says Custer Feldspar, 20%. Well, it's a good idea if you can, to realize that Custer Feldspar is a potash feldspar. Because suppose you don't have any Custer Feldspar, but you have a different kind of potash feldspar in your glaze kitchen. Well, you might be able to substitute the other kind of feldspar in the recipe, as long as you know that they're both potassium potash feldspars. Okay. Another common potash feldspar that you can buy now is called G200, a really imaginative name. G200. So G200 and Custer are both brand names or product names for a type of potash feldspar. Yeah?
Is a Minspar?
Minspar, yep, good segue. I appreciate segues, that's a good segue. Minspar 200 is a brand name for a soda feldspar. And again, so it can get a little confusing because Minspar 200 is soda, but G200 is potash. Because they don't care about being confusing. Okay? So this is why it really helps in a recipe then, again, if you're interested in this, to get familiar with some of these names, because then you can recognize and say, oh, that's a soda feldspar. And say, in some cases, they might just say soda feldspar, and they leave it up to you as the person making up the glaze to pick whatever soda feldspar you want to use. It varies, depends on the recipe. The next one I've got listed there is Nepheline Syenite. That's a rock. And a rock, by definition, is generally considered to be a combination of two or more different minerals. Now, you can have rocks that are made out of one mineral, but generally, they are made up of more than one mineral. And the point there is, now, if I get Nepheline Syenite, which is a rock from different sources, there's a good chance it's not going to have the same composition, because who says it's going to have the same proportions of the minerals that are in it? So I can write a formula for a mineral, but I can't really write a specific formula for a rock. Okay? And Nepheline Syenite is a rock. I've got an example back there. And it contains several different kinds of feldspars, plus the mineral nepheline, so it contains at least 3 minerals. But again, the main thing is it's used as a flux. And it's a source of sodium. It's a source of sodium of the flux. The main reason why we use it, this complicated rock, is because it contains sodium oxide. That's the oxide. That's what we really want out of it. Okay? The next two that I've lumped together, they're Cornish stone and Cornwall stone. Those are the same thing. You might see it written either one of those ways, depending on who wrote the recipe. Cornish stone and Cornwall stone. That's basically it's a rock. It's a rock imported from England. And if you think about it, we've gotten pretty spoiled. We can afford to dig up rocks in England and crush them and ship them over here and buy them and use them in our pottery and still get it at a reasonable price. It's crazy. And this, is used primarily as a source of a flux, and it contains sodium and also contains some potassium. And it's kind of like, there's a rock, I don't know whether you're familiar with the rock granite. I've got an example back there. It's kind of like an old type of weathered rock that has sort of partially decomposed, but it contains some of the feldspars. It's not horribly different from Nepheline Syenite. It's a little different, but it contains a lot of sodium and potassium. So far, all of these things we're using primarily because they give us fluxes. Cornish stone also gives us fluxes, sodium and potassium. Remember, if you keep this table handy that I had with the fluxes, you can refer to that. So when I start talking about fluxes, which one are fluxes? Okay? The next one, spodumene, is a mineral. And that contains the flux lithium. So we use the mineral spodumene because we want to get the lithium oxide that's in it. And I've got spodumene back there on the table. It's a nice looking mineral. And related to it, but slightly different, is the mineral petalite. That's also a mineral. So I can write a very specific formula for these minerals if I care about the formula. But the difference is that spodumene and petalite have slightly different proportions of lithium in them, so I can't substitute one directly for the other. And petalite isn't used as much anymore. It's become a little more rare, a little more expensive. I think years ago, I remember in the 60s and the 70s, number of years ago, in the 60s and 70s, it almost seemed as if there were famous potters who would write recipes purposely using obscure ingredients, maybe so you couldn't copy them or something, or because there was a certain panache to using, obscure ingredients. And so there are a lot of recipes written with petalite, and there's no good reason to use it. If spodumene is a lot more readily available and it's cheaper, why not write it? Why not use it? But anyway, so you'll see recipes with petalite, and it's kind of difficult nowadays to get petalite, and it's more expensive. But they both are sources of the flux lithium, which is why we would use them. Okay, now everything so far we've been talking about have been used for fluxes. Now we get to a different category. Flint, silica, and quartz, it's all the same stuff. And this is our glass former. This is what the bulk of the glaze is made out of. Flint is the name, and I have examples over here. Flint is the name for a sort of slightly impure form of quartz or silica, and it was originally, you'll see flint listed in a lot of English recipes because traditionally England didn't have deposits of quartz like this. We do in the United States and other parts of the world, but they didn't. And you're probably familiar with the chalk cliffs of Dover. Well, chalk is limestone, but in the limestone deposits there were lumps of silica that would form. And if you walked along the base of the cliffs, there'd be all these pebbles at the bottom of the cliff because the limestone would erode and wash away and wash down into the ocean. And these pebbles would erode and roll down the face of the cliff. So there'd be this rubble all along the bases of these chalk cliffs of these pebbles of flint. And that was the only significant source that the English potters had for silica. So they'd gather up these flint pebbles. It's the same flint, by the way, you've heard of that's used for making Native American and arrowheads and things like that. Same material. But that was the only source they had. So in the English recipes, when they used silica as an ingredient, they listed it as flint because they were grinding up pebbles like I have back there, and that was their source of silica. So flint is just another form of silica. In this case, usually it's found as pebbles like I have back there that they grind up. Quartz is the actual name for the commonly occurring mineral. The mineral name for this is quartz, and it's made of silica. Okay? So those are all the same thing. So you might see a recipe that calls for quartz, or it might say silica, or any one of the three. Same stuff. Okay? So clays, the next category are clays, and there are whole lots of different kinds of clays. And again, believe it or not, clays are actually, there are specific clay minerals. I can write a formula for different types of clay minerals. It's not just sort of general garbage pail of elements. There are specific minerals. And in our clay bodies, as well as that we make things out of, as well as our glazes, we use particular types and mixtures of these different clays. And some of them, not all of them, some of them we use in glazes. So the first type is China clay or kaolin. Again, that's the same stuff. China clay is the common name for kaolin. That's a specific kind of clay. And it's a fairly pure clay, and that's one of the reasons why we like to use it in glazes, because it doesn't have a lot of impurities that are going to affect the color. Now, I think I mentioned earlier that the reason why we use clay is because it contains silica and aluminum oxide. And the real reason why we use the clay is to get this, the aluminum oxide. And what's the aluminum oxide? Stabilizer, right. So even at this point in the list, we've had a number of possible fluxes. We've had the silica, for the glass former, and now we've got clay, which will provide a stabilizer. So we've covered, even we haven't even gone down the list away, but we've covered all the three categories that we need to make up a glaze. Okay? And those two terms that I have underneath it, EPK and Grollig, I think you have Grollig on your list, right? I think, did it not? Okay, I couldn't tell. Grolleg, Grollig. Those are two basically brand names of kaolin. EPK is mined in Florida. It stands for Edgar, EDGAR, Edgar Plastic Kaolin. EPK for short, Edgar Plastic Kaolin. Edgar, like the man's name, Edgar Plastic Kaolin. And Grollig is an English kaolin mined in England. So again, here we dump this dirt in a boat and ship it over and buy it. And the Grollig happens to be a little different particle size. The size of the particles is a little different, and the purity is a little different than EPK. So there may be advantages to using one type or another in the glaze. But the main reason is all of these kaolins are fairly pure, so they're not going to affect the color. So while we're getting the aluminum oxide, we're not going to get a lot of iron, for example, or something else that's going to change the color of our glaze, which we want to control the color ourselves, not have it dictated to us by all these impurities. Okay? Ball clay, the next one down, is another category. It's another type of clay, and it has a lot of uses. It's a very, very, very fine clay. Typically, it's added to glazes. Not so much to get the aluminum oxide, but to actually, this is a good example of where we use ingredients for different purposes. A lot of the reason for adding ball clay, this very fine clay to a glaze, is to give the glaze strength when it's dried. Maybe you've all seen a glaze that when it's dried on the pot, it's kind of powdery and hard to handle and it comes off on your hands or it flakes off. So in addition to all these other properties that we want a glaze to have, the pots have to be handleable. So ball clay a lot of time is used because it's fine. It almost acts like a glue so that when the glaze dries, the surface of the glaze is hard and I can handle it and it's not so powdery and fragile. It still gives me the aluminum oxide I want, but it has this additional property of sort of helping to harden the glaze. But it's not as pure as kaolin. So I wouldn't necessarily want to use a lot of ball clay because it would introduce these other impurities that would affect the color. But I could put a little in to help harden the glaze. Okay? There are lots and lots and lots of brand names for ball clay. One of the common types you'll see is called OM4. Again, another imaginative name. That's a really common brand name like Scotch tape or Kleenex for a type or a grade of ball clay, OM. And again, the recipe will just say OM4. It won't say OM4 ball clay. So if you see a recipe and it says OM4 and you're making up glazes, you really want to know that OM4 is the type of ball clay because there might be dozens of other ball clays out there that you could substitute just as well if you don't happen to have any OM4. Okay, the last type, Bentonite, this is another kind of naturally occurring clay. This is actually formed in the ground from volcanic ash. And it's really, really, really fine clay. I mean, so fine that you can't make anything out of bentonite. When you mix it with water, you get this sticky mass. So you can't do anything, you can't make anything out of it. But it's added to glazes in very small amounts to help the glaze, to stop the glaze from settling out in the bucket. Here's an example of a glaze ingredient that has nothing to do with the final glaze properties. We don't want it to affect the final glaze. The only reason why we add bentonite is to keep the stuff from settling out in the bucket. So typically we don't add a lot of it. Normally you wouldn't want to add more than 2% to a glaze. And it's not an extremely pure glaze, so you'd be contaminating the glaze if you used a lot. And if you added a lot of it, you'd really cause problems for your glazes. And you'll see later on, I've seen some glaze recipes that have 5, 6, 7% bentonite, and they're almost unworkable. And one of the reasons why is this stuff is so fine, it absorbs a lot of water. So when the glaze dries, it shrinks and cracks and falls off the pot. So it's a great sort of sticky goop to help hold the glaze in suspension while it's in the bucket. But when the glaze, because it holds a lot of water, but when it dries, it shrinks like crazy. And then the glaze cracks and shrinks and falls off, or it can also cause crawling of the glaze. So this is an additive which is only like what you call a processing additive. we don't care if it ends up in the final glaze. It does a little bit, but that's not why we're adding it. We're adding it to help us make the glaze rather than what the glaze is going to come out like. The next group here we've got is limestone, whiting, chalk, and calcite, all the same stuff. It's all, I think my board's getting full enough here where I can erase this. Chemically, and that's what we really care about, chemically these four things are all the same. They're all calcium carbonate. And if you're interested in the formula, it's this, CaCO3. And so what we really want here, it's the calcium, this contains calcium oxide. Another way to write this formula is this. This makes it a little easier to see what it's made out of. It's actually made out of calcium oxide and carbon dioxide. And so the reason why we use this stuff is because this is what we want. We want the calcium oxide. That's one of our fluxes. And so limestone, when it's called limestone, that's the rock. That's a rock, and I've got a chunk of it back there. Matter of fact, you may be aware there's a huge limestone quarry right in downtown Frederick, on the east side of Frederick by Route 70 there. It's a big limestone quarry there. Whiting is the old name. Years ago, before they even knew a lot about chemistry, all they knew was that if they took this rock and ground it up and you mixed it with a little fish glue, it made a really nice white paint. So things were named by what they did. Whiting, it makes things white. Same stuff, it was powdered, ground up limestone. So you'd add a little glue to it, typically fish glue or horse foot glue or something like that, and you had paint. Chalk, that's the English name because the form of limestone that was most common or very common over in Britain was these chalk, like the chalk cliffs of Dover. And that's just a fine-grained version of limestone. It's just a sort of but so that's the same stuff. And calcite is the actual mineral name. So like we said, like quartz was the mineral name for silica. Calcite, it's not the only one, but it's the most common one. Calcite is the mineral name. So most limestone rocks are made of the mineral calcite. But it's all the same stuff. It's all this. It's all calcium carbonate. And it's the calcium oxide that we want. And the great thing is, this is a great flux. It's really common, and it's really cheap. And you can get it very pure. So this is one where we got lucky, at least on this one. This is good stuff. It's cheap, it's pure, it's easy to get. Okay, the next one, and again, I have examples of all. The next one, dolomite, is a little different. It's a rock like limestone, and it's also, this is a weird thing. The rock is called dolomite, but the mineral is also called dolomite. Nobody ever said geologists were totally systematic or logical about all of this stuff. But the difference is, now this is a magnesium calcium carbonate. Dolomite. So in addition to containing calcium, it contains magnesium. And the real reason why we use dolomite is to get the magnesium. Magnesium is not that common in nature in a form where we can use it. And it's a great flux to have in glazes, magnesium oxide. So we use dolomite primarily to get it contains calcium and magnesium oxide, but we use it to get the magnesium. And one of the major uses for magnesium in a glaze is to make a satin glaze. A lot of the most common cone 6 and cone 10 satin or satin matte glazes are that way because they contain magnesium. And again, we're lucky because magnesium, in other forms of magnesium or magnesium oxide, are really expensive. They're hard to chemically process, and here we've got this dolomite, which is really cheap. By the way, if you ever buy, quote, lime to put on your lawn, it's dolomite. So it's really cheap and really readily available. So here's a case where we're really lucky. This somewhat, it's not exotic, but this difficult sometimes to obtain element, magnesium oxide, it's readily available. So that's one of the reasons that's why we can easily make satin glazes or satin matte glazes. The next one is a mineral called wollastonite. And this is another source of the flux calcium oxide. And you might say, well, wait a minute, we already have a source of calcium oxide, a great source. We have limestone, so why do we need wollastonite? And this is another good example of sort of the thinking about glazes, is that calcium oxide as a flux really only becomes effective when I say effective, I mean it's starting to cause melting at fairly high temperatures. So suppose I want to make a glaze that contains calcium that at lower temperatures, like cone 6 instead of cone 10, a lot of calcium is not going to work. It just doesn't chemically react at low temperatures. Wollastonite does. Wollastonite is a calcium silicate, which means it contains calcium oxide and silica. And because it's a different chemical form than the limestone, it melts at a different, and in fact, it melts and reacts at a lower temperature. So a lot of cone 6 glazes, is everybody familiar with the notation of cones, by the way, before I go to, like cone, low temperature and cone 6 and mid-range and high? Everybody comfortable with that? Okay, so a lot of cone 6 glazes might contain wollastonite, where they won't contain a lot of limestone, because the limestone doesn't work effectively that much, huge amounts at cone 6. Whereas wollastonite melts and acts as a flux at lower temperatures. So it gives us a choice now in terms of raw materials for a particular glaze or a particular use. And you can get it, it's fairly pure, it's fairly cheap. The next one I have on the list, the next two I have on the list here are Alberta Slip and Albany Slip. These are actually clays. Well, actually, Albany Slip is a clay. And this is what's really interesting about this is a clay, a dark brown clay that was dug up around Albany, New York. That's where the name came from. And the interesting thing is that this clay contains all the ingredients you need to make a glaze. So this was used extensively in the earlier days of pottery in this country and all over the world, because all you need to do is take the clay and mix it with water and make a slip out of it and put it on your pot, fire your pot to cone 10, and you have this beautiful chocolate brown, mahogany brown glaze. Because that clay itself, it's a very impure clay. So it contains a lot of silica, it contains a lot of the fluxes, and it contains all the alumina you need in just the right proportions to make a perfect cone 10 glaze. So in fact, was a really, really valuable glaze ingredient, or glaze, because if you think about it, when potteries were starting, a pottery might be started, somebody would find a clay deposit, and as long as there was a wood supply and a water supply, that's where they set up their pottery. Usually the potteries were located wherever the clay was, so they wouldn't have to transport it too far. So, but then what did you do about glaze? How would you glaze your pots? Well, if you could get some of this Albany Slip, that's all you needed. You didn't need to make chemicals, you didn't need anything. All you needed was this one clay. You'll see it a lot if you go to antique shops. If you see it on these old crocks or jugs, that's this dark, it's typically used on the inside and the top of the outside. It's this dark, beautiful mahogany brown, sort of chocolate brown, shiny glaze. That's Albany Slip. It also used to be made on telegraph insulators. I don't know, anybody collects insulators, that beautiful brown, it was put on porcelain insulators for telephone poles and electrical lines. That was Albany Slip. And it was shipped literally all over the world. So it was mined in Albany, New York, shipped down the Hudson River. We're talking the 1800s, and shipped all over the world because it was such valuable dirt, basically. Well, it also was used because it contains a lot of iron and manganese, and it made a great glaze colorant. So it was also used as a glaze ingredient. You could put it into a base glaze, and then add some Albany Slip to it and and produce a nice brown glaze. So it was used as a modifier, a colorant to the glaze. So it appeared in a lot of glaze recipes. And it's been used for a long time. And of course, then a long time ago, the pits in Albany, the clay pits basically ran out, and then the state also decided to put a housing project on the site. So that was the end of digging up Albany Slip. So people literally were panicking because there were commercial potters, production potters, whose whole production depended on Albany Slip for their glazes. So a number of chemical companies stepped forward and said, okay, we can produce maybe a substitute for it. We'll combine other ingredients and produce something that has about the same properties, and that's what Alberta Slip, that's one example of it. Alberta Slip was developed out in Montana, and it was one example. It's basically a combination of clays and minerals that has close to the same properties as Albany Slip, as Albany Slip. Now, in this case, it's not naturally occurring. It's a bunch of materials mixed together, whereas the Albany Slip was literally just dug up out of the ground. Okay, and it's mostly used nowadays. It's mostly, if you still use it, if people have a recipe for a glaze that calls for Albany Slip as the colorant or one of the ingredients, you could substitute Alberta Slip. That's the idea. And it's called a slip, even though it's a clay. This is, again, this imprecise terminology, because the only thing it was used as was a slip, basically. That's the original use. Everybody know what a slip is? Basically, a slip is just clay and water, made up to sort of a thin, watery consistency. So that's the only way it was used. So you didn't make things out of Albany Slip clay. Again, it was too fine-grained. It was like super fine-grained earthenware. So you didn't make anything out of it. It was only used as an ingredient in other things, or as a slip by itself to make a glaze. But the point I wanted to make also, and you'll see later on when we start talking more about this, if you're interested in glazes, it really is useful, if you can, is to start to familiarize with yourself with some of these things, so that when you look at a recipe, you can recognize. For instance, you can look at a recipe and say, for instance, that this glaze is going to craze. If I look at a recipe and I see it has a lot of Nepheline Syenite in it, I can guarantee that alone, because it has a lot of sodium causes crazing, I can look at the recipe and say, that glaze is going to craze. I don't need to test it, I don't need to do anything, I can just look at the recipe and say, that's going to craze. And so it really helps for a lot of different reasons, as you'll see. It helps you if you can become a little familiar with some of these ingredients, in terms of like substituting ingredients, or in terms of understanding what the glaze is going to do. Okay? Okay, so on the second page is Gerstli borate. Underneath that on your copy, do I have Gillespie borate and Laguna borate? Okay, I couldn't remember. I've been editing these constantly every year, so I don't know where my edits appear in copy. Gerstli borate is basically a naturally occurring kind of dirt. I'm being sarcastic here, but it's a naturally kind of dirt that contains a lot of boron oxide, which is why we use it. Boron is an element, a very light element, and boron oxide, another one of our oxides. The formula, in case you're interested, is B2O3, boron oxide, and it's a great flux. It's a terrific flux. So this is a kind of ore, I'll be generous and call it an ore, that was mined in California, and it was discovered by a miner whose name was Gerstli. So originally it was called Gerstli's borate. And a lot of, as you're probably familiar, out in California and Nevada, that area, there's a lot of these borate minerals. 20-multene borax, you've probably heard of, that's mined out there. There were a lot of these boron mineral deposits. And so they found this stuff called, this ore called Gerstli borate, and when it's a great flux for putting in pottery. It's a terrific flux. So it's cheap. It was used a lot over the years. It's in thousands of glaze recipes, probably, mostly cone 6 glaze recipes. And especially when cone 6 became increasingly, cone 6, by the way, was created artificially, to sort of reproduce, to get the same results as cone 10, but at a lower temperature. And it was really developed because of the oncoming of the electric kiln. Most naturally occurring clays are either low fire or high fire. And the whole field of cone 6 was really created around the use of an electric kiln, so that you didn't have to go to higher temperatures, but you could get similar results. So when cone 6 became really popular, Gerstli borate became really popular because it was such a great flux for using in glaze recipes. The problem was it was a relatively small mine, and U.S. Borax that owned the mine, that bought the mine, decided to close it, 10, 15 years ago. So again, there were potters literally committing suicide, jumping off of bridges. Maybe not exactly, but I knew potters, when I lived in Maine, there were potters that their whole production, they were cone 6 production potters, and every single glaze they used depended on Gerstli borate. And all of a sudden they said, sorry, we shut the mine down. And so again, what happened was a number of chemical companies said, aha, I can make a buck out of this. So which is good, but they stepped up and they started making substitutes for Gerstli borate. One of them was called Gillespie borate. So that's a product made by the chemical company Hamel and Gillespie. So they called it Gillespie borate. And Laguna borate is made by Laguna Clay Company. And there were others. So there were a number of companies that came forward and said, okay, well, we make this substitute for Gerstli borate. Well, not too long after the substitutes came out, Laguna actually bought the rest of the mine, and they reopened the mine. And they said they still have enough of a stockpile to last about 100 years. Eventually, it's going to run out. But so you can still buy. Gerstli borate is back on the market. People kind of came back off the ledge, and you can buy it. And so I don't think these substitutes are as popular now, because you can still get Gerstli borate, but it is going to run out. It's not going to last indefinitely. And the other thing was, for some of the reasons that I mentioned before. The substitutes were never exactly as the same as Gerstli borate, partially because Gerstli borate is, I was sarcastic calling it dirt, because it's really, really impure material. And so a lot of the impurities were what made it great. And so it was kind of difficult, and including its effects on color and everything else. So it was difficult to duplicate exactly from a theoretical point of view, because there was a lot of these sort of uncertainties that really made it good. But you can still get it. You can still get Gerstli borate. Borax, the next one, that's a mineral. That's another one of those boron minerals, boron oxide minerals. That's what 20-mule team borax is. It's the mineral borax. And it's used as a water softener, and it's used for laundry and cleaning. And it used to be used in glazes, especially raku glazes. And you might see old raku glazes that call for borax. Don't use a recipe that contains borax. Because the problem is the mineral itself contains water. And the problem is that it melts before the water comes off from the mineral. So when you heat up borax, it foams up and bubbles and makes a mess. So they used to, if you had raku glaze, has everybody or anybody done raku? And you know how you look and you watch the glazes melt? Well, if you had a borax glaze, you'd watch the glaze and it would start to melt, and then it would start to foam up, and you could get a half an inch of bubbly, foamy looking stuff, glaze, sitting on the top of the pot, which then starts to slide down the pot. And so that if you watched it, and if you were lucky, the bubbles would pop, and the foam would kind of quiet down, and eventually all the bubbles would collapse, and you'd end up with a nice glaze coating if you were lucky. But in the meantime, it's sliding off the pots and landing on the bricks. It made a mess. But it was the only common, cheap, practical boron source. So nobody that I know uses it for glazes anymore, but you still see it in a lot of recipes. And the thing you could try, if there's something unique about the recipe, you could try substituting Gerstli borate for it, just directly to start, and then go from there. But the other thing is that most raku recipes are so simple, it's not worth messing and adjusting an old glaze. There are so many recipes out there, it almost isn't worth messing with it. If I see a borax recipe, I just file it. And I'll say, I can find a better recipe than that, because they're not complicated. Okay? Colemanite, that's another boron mineral that used to be used in glazes. And it was fairly pure, and it was and there is colemanite in Gerstli borate, but colemanite was a mineral by itself, but the problem is it's not available anymore. The only way you can buy it is if you buy a shipload from Turkey, because industry still uses it, but it's not mined in this country anymore, so you really can't get it. But again, you'll see a lot of old recipes that call for colemanite, and so that's what it is. It's a boron, it's a source of boron, the flux. And again, you could try substituting, if there's something about that recipe that you just have to use it, you could try substituting Gerstli borate. And you're going to have to do some testing probably and some adjusting, but that would give you a start. Just swap in Gerstli borate to start and take it from there. Soda ash. This is basically sodium carbonate. This is also called washing soda. And you can buy it in a grocery store. Soda ash. It's called washing soda. Chemically, it's sodium carbonate. Or, like the calcium carbonate, it's sodium oxide and carbon dioxide. Well, with the limestone, it's calcium oxide and carbon dioxide. This is sodium oxide and calcium oxide and carbon dioxide. And again, so we use soda ash for the sodium oxide. But this is not something we want to use in most glazes, because it's water soluble, very water soluble. And we don't generally want to use water soluble ingredients in glazes. Can anybody guess why? There are a few exceptions, but in general, you do not want water soluble ingredients in a glaze. The problem is that when you put a glaze on a pot, you've got the wet glaze on the pot, right? And then the glaze dries. Well, what happens is, when the glaze dries, the water is moving to the surface of the glaze and evaporating, right? Well, if the sodium carbonate is dissolved in the glaze, then it moves with the water to the surface of the pot, and you end up with a crust of sodium carbonate, because it can't evaporate. So it migrates to the surface with the water, and then the water evaporates, leaving the sodium carbonate on the surface. So you've made this really nice, carefully well-mixed glaze, and now the glaze is unmixed on the pot. All the sodium carbonate's on the surface. So we don't want water-soluble ingredients in glazes because when the glaze dries, they migrate with the water and they move around and they're no longer where they were originally. They're no longer all throughout the glaze. They're typically right on the surface. Now, the only exception to that is this is the main ingredient. You may have heard of carbon-trapped Shino glazes. This is the ingredient that's used in carbon-trapped Shino glazes to make them carbon-trapping. And we're taking advantage of the fact that it migrates, but in most glazes you don't want it. So you say, okay, well then if it's a great source of sodium, which it is, it's pure, it's cheap, it's readily available, this is why we don't use it. This is why we use Nepheline Syenite. That gives us the sodium. This is why we use soda feldspar. That gives us the sodium. That's why we have these other rocks that we use instead, not because they're any more pure or anything else, but they don't dissolve in water. So I can use Nepheline Syenite to give me my sodium where I don't want to use soda ash. The next group, these are all the same thing. Red iron oxide, red ochre, hematite, ferric oxide. This is a colorant, right? This is one of the main colorants that we put in glazes. Red iron oxide, that's the most common term that you'll see in a recipe. They'll call for red iron. Red ochre is a mineral term, and I've got some red ochre back here. That's just the name that's given when it's found in the ground as a mineral. It's called red ochre. And an ochre, there it is. And an ochre, this is like Vanna White, right? An ochre is just a geological term for a soft, powdery mineral form, which is and that's the way it occurs naturally. Hematite is the mineral name for this stuff, and ferric oxide is the chemical name. Chemically, it's this. I don't want to drive you crazy with formulas, but that's what the chemical, and that chemical is called ferric oxide. So they're all the same thing. So you may see, I don't know that I've ever seen I've seen red ochre. You may see any one of those terms in a recipe. Hematite, you're not going to see very often, but the most common is going to be red iron oxide. But it's all the same stuff, and it's all primarily a colorant. So it generally would not be listed in the base glaze. It would be one of those things below that's added below as an additive to the glaze. Black iron oxide, the next group, that's another form of iron oxide that you'll see in some glaze recipes. They'll specify black iron oxide, and it's black. Magnetite is the name for the mineral that is black iron. Magnetite is black iron oxide. It's just a different form of iron. And with a lot of things, I found with pottery is that you don't necessarily need all these raw materials, but it's almost like out of curiosity. Potters want to try things to see what I get. So you don't need black iron oxide to get iron oxide in your recipe. Red iron oxide works just fine. There may be some different impurities in black iron oxide so that when you use it, you might get a slightly different color from it because of the impurities. One of the problems I found is that black iron oxide is not as reactive in a recipe. So you might, instead of spreading out in the recipe and giving you a nice color, you might get specks in your glaze. Now maybe you want that. So maybe you'd want to use black iron oxide because you want specks in the glaze rather than a uniform color. So it doesn't behave exactly the same as the red because it's a different chemical or different form, but it still is a source of iron oxide. But you really don't need it. Unless there's a recipe that you're in love with, and the only way you can get that effect is with the black iron oxide. But other than that, red iron oxide works just fine. Yellow ochre is another form of iron oxide that's naturally occurring. It's a soft, powdery material. But it also, the minerals that are in it actually contain a little bit of water, and it generally is not as pure as the red form. So one of the reasons to use yellow ochre as a colorant, maybe instead of red iron oxide, is really for the impurities. And if you noticed, you probably don't remember, but early on in the talk, I had that recipe for green crackle, and the colorant in green crackle was yellow ochre. The reason why is, with the yellow ochre as a colorant, I get a nice kind of yellowish green to that glaze, where if I substitute red iron oxide, I get a slightly bluer green. So there's a case where it's the impurities, and I don't know what they are. You'd have to have it chemically analyzed. But there's something in the yellow ochre which gives me a different shade of green in the glaze than the red iron oxide does. So it's not because it's any better or any cheaper, but I'm using it strictly for this subtle difference in color that I get with a different form of iron oxide. And that's just a matter of experimentation. You can't really predict that. You just need, if you have a glaze that you like that has iron and you want to just play with it, try some of the other forms of iron oxide and see, maybe you might get a slightly different color out of it. Rutile So we're getting down into color, at least for this point, we're getting into some other colorants. Rutile is another natural occurring mineral, and I've got a rutile crystal back there. Rutile. And rutile consists, one too many. Rutile consists of titanium oxide, TiO2, plus some iron oxide right in the same mineral as a naturally occurring impurity. And rutile is used as a colorant. There's a whole family of glazes called rutile blues or floating blue, cone 6 floating blues, and it can give you sort of an iridescent watery blue color. It also, the titanium oxide forms another, remember, look at the form of this, like SiO2. It forms another glass in the glaze, and it produces kind of a watery effect to the glaze. So it's used as a colorant. It's used as a stain. By itself, rutile powder is kind of a mustard yellow color. It's used as a stain or a wash on the surface. It's pretty versatile stuff. Used as a stain on the surface of pots, as a colorant in glazes, as a modifier in glazes.
The Potter's Roundtable is brought to you by Washington Street Studios and our patrons. If you enjoy the show, please subscribe, give us a 5-star review, and tell your friends. If you want to learn more about Washington Street Studios and shared studio memberships, please visit our website at www.hfclay.com. Thank you, and we'll see you again next time on the Potter's Roundtable.